Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the VLSI technology. In that we are discussing the chemical vapor deposition in the dielectric thin films, and today our topic of the day is the dielectric CVD processes. We are going to talk about all of the processes in the dielectric chemical vapor deposition, and we have classified all of them in some different videos. So we are going to do the in-depth analysis of all of these processes. So it is very difficult to talk about all of these processes in a single video. So we are going to talk about all of these processes in some 2 to 3 videos. So I hope you will be staying with me till the end of all of these videos and you will be getting to know all of the dielectric CVD processes in detail. So there is some small requirement that you go back and watch all of the CVD and the dielectric thin film videos that I have already discussed previously. If you have still not watched them, go and watch them first and then come to this video. So let's start with the dielectric CVD processes. We are having different dielectric CVD processes. So these are all the dielectric CVD processes that we have. But today in this video we are not going to talk about all of them. We are going to see the in-depth analysis of some of these dielectric CVD processes. So we have thermal Silane CVD process. We know what is Silane. Then we have thermal TEOS CVD process. I hope you know now what is TEOS. If not, you have still not watched all of the previous videos with great attention. You know now the structure of TEOS, then we can proceed. So then we have PECVD Silane processes, then we have PECVD TEOS processes, dielectric HBAC process, ozone TEOS processes, then we have spin on glass, then we have high density plasma chemical vapor deposition. So all of them we are going to analyze in depth. So first of all we have the thermal Silane CVD process. Now we know what does the word thermal means. It is meaning at a high temperature. We know what is Silane. Silane is SiH4. So at the high temperature, Silane is reacted with the oxygen to form the SiO2. SiO2 is a dielectric. So we are doing the dielectric deposition of SiO2 with the help of Silane and the oxygen. So at the high temperature, SiH4 plus 2O2 is going to give me SiO2 plus water vapor, right? This is the full reaction that we have. So now Silane has been commonly used for silicon dioxide deposition with both APCVD as well as LPCVD process. If you have watched all of the videos on the CVD, now you know what is APCVD and also you know what is LPCVD. APCVD is atmospheric pressure chemical vapor deposition and LPCVD is low pressure chemical vapor deposition. Now when I am using the APCVD, we can use the diluted silane, which is 3% silane in nitrogen, right? So now the silane is a costly substance. Whenever I am using diluted silane, the cost will be reduced. So now when I am using APCVD, the cost is reduced. But whereas if I am using LPCVD, I have to use the pure silane. So it is not commonly used in the advanced fabrications of the VLSI chips, right? So this was all about the thermal Silane CVD process. Coming to the thermal TEOS CVD process. Now we know what is TEOS. We know its structure. It is SiO C2H5O. Thermal means at high temperature. So at 700 degrees Celsius, the TEOS is dissociating to form SiO2. This is our dielectric. Plus we are forming some volatile organics. So whenever I am using the TEOS, I am going to do the physiosorption, right? I am not going to do the chemosorption. So physiosorption, I hope you know what it is. So what are the advantage of physiosorption, that also you know, right? So it is having high surface mobility, and whenever I am having high surface mobility, I have already discussed about this concept that whenever I am having high surface mobility, I am going to get the good step coverage. So TEOS film has a better step coverage than the silane. So this is the advantage of using the TEOS over silane. So we have already talked about this reaction. So it is done using the LPCVD, low pressure chemical vapor deposition. Here the TEOS is dissociating at a higher temperature to form SiO2 and the volatile organics. So now for the formation of PMD, we are using the borophosphosilicate glass with the trimethyl borate and the trimethyl phosphite. And if I am using it for the IMD, then the temperature must be too high. Okay, so coming to the PECVD silane processes. Now you know what is PECVD? PECVD is plasma enhanced chemical vapor deposition. We know what is silane, so a lot of things now we know about it, but there is a small thing that you need to remember, that we are using the laughing gas here with silane. So whenever I was using the thermal silane process, there I was using silane with O2, but here I am using silane with laughing gas, that is N2O. So silane is going to dissociate in the plasma to form SiH2 and the oxygen radicals. So whenever I have the radicals are very reactive, they are going to react rapidly to form the SiO2, right? So here I have the SiH4, which is silane, plus the laughing gas N2O, so it is going to form the SiOxHY in the presence of plasma as well as heat, and we are forming another volatile compounds like H2O, N2, NH3 and so on. So now here we need to overflow N2O using SiH4 level constant to control the deposition rate. We cannot do the vice versa of this. So the question is, can we overflow silane and use nitrous oxide flow rate to control the deposition rate? As I have already told you, we cannot do the vice versa. We cannot overflow silane and use nitrous oxide flow rate to control the deposition rate. Why? Because first of all, silane is very costly, it is dangerous, and also it will be explosive, right? So theoretically we can, but practically we should not even try this. Why? Because it is dangerous and not cost effective, and overflowing silane will create a big safety hazard like fire and explosion because it is explosive. So silane is more expensive than nitrous oxide, so we are going to overflow the nitrous oxide only, we are not going to overflow silane. So coming to the passivation with the help of silicon nitride. So passivation means we are going to stop the mobile ions from entering the chip. So it is a barrier layer that we are forming for the moisture and the mobile ion protection. Moisture or mobile ion can go and hinder the normal working condition of the VLSI chip. So we need to have a passivation layer over it so as to protect it from moisture and the mobile ions. So now we are using the PECVD nitride to make it as a passivation layer. But whenever I am using the nitride as a passivation layer, below that first we have to use the oxide layer. I am going to tell you what is the requirement of oxide. So whenever I am using nitride, below that always and always I am using the oxide layer. So first of all, the PECVD nitride deposition is occurring at a low temperature which is lesser than 450 degrees Celsius. So here we are getting the high deposition rate and we are using the silane, ammonia and the nitrogen. So silane, ammonia and the nitrogen, SiH4, N2 and NH3 in the presence of plasma and heat is going to form SiNXHY plus H2 plus N2 plus NH3. So here what we require a good step coverage. So as to get a good barrier layer, we require high deposition rate, we require good uniformity, also we require stress control. So for the stress control only we are using the oxide layer below the nitride layer. The nitride layer is going to give a good stress, and to prevent our chip from this stress from the nitride layer, we are going to use a thin oxide layer below the nitride layer so as to work it good or efficiently as a barrier layer. So what is the process for this passivation layer deposition? First of all, we are going to do the first stabilization. We are going to stabilize the pressure, then we are going to do the oxide deposition, right? So as I told you, first of all, we have the thin oxide layer, which is going to give me stress buffer from the nitride layers. Nitride layer is going to give a big stress towards the chip, and we don't want that, okay? A lot of deformities can caused with the help of the high stress from the nitride layer. We have to avoid that, so we are forming the first oxide layer. After that, we are going to do the pumping, and then we are going to stabilize the pressure again. This is called the stabilization 2. Okay, then we have the nitride deposition. This is our actual passivation layer deposition, and after that we are going to do the plasma purging to eliminate the SiH4, and again I am going to do the pumping. So now coming to the EPROM passivation dielectric. So whenever I am using the erasable programmable read-only memory, and there I am using a passivation layer, so there must be some characteristics of this passivation layer. So whenever I have EPROM, what is the characteristic of EPROM? EPROM requires UV light to erase the memory, right? So UV light must go to this chip. So here our passivation layer must be transparent to the UV light, otherwise the passivation layer is going to hinder the UV light to reach the chip as well, and we cannot erase the chip with the help of UV light. So what we require UV transparent passivation layer, because UV light can erase the EPROM memory. That is our requirement. So what we are using the oxynitride as the passivation layer. So here I am using the source gas as Silane, N2 ammonia and N2O. So you can see whenever I have plasma in the high temperature and the source gases as Silane, N2, NH3 and N2O, then I am forming the oxynitride SiOX, NY plus H2O plus N2O plus some other volatile compounds. So here if I am using the oxynitride, it is having the properties in between oxide and nitride. First of all, the very big advantage of using the oxynitride is that it is UV transparent that we require, and it can be used as a good barrier layer. So now coming to the PMD barrier layer. So we are using phosphosilicate glass or the borophosphosilicate glass, and we are using a diffusion barrier layer. So we will be using the undoped silicate glass with 1000 angstrom thickness. If I am using the low pressure chemical vapor deposition of nitride at nearly 700 degrees Celsius, so we can use only 300 angstrom thick layer. If I am using the plasma enhanced chemical vapor deposition of nitride at lesser than 550 degrees Celsius, so I can use lesser than 200 angstrom thin film. So at higher temperature, PECVD nitride film has a higher deposition rate and lower hydrogen concentration and the better film quality. So these are all of the advantages of using the PECVD over LPCVD and APCVD. So this is the possibility of using it in future in the remote plasma CVD. So coming to the dielectric anti-reflective coating. So whenever I am using the anti-reflective coating, it is going to give me high resolution for the photolithography. So the photolithography process is using the light, and if the light is going to reflect, it is not going to give me the good results. So we require the anti-reflected coating so that the light is not going to reflect as much as it was reflecting previously. So ARC layer is required to reduce the reflections. We can use the metallic ARC as well, in which I have used the titanium nitride. Okay, so it is going to reduce the 30 to 40% of reflections, but it is not a good technology to reduce the reflections if I have lesser than 0.25 micrometer feature size. So here I can use the dielectric ARC. So dielectric ARC layer is formed using the chemical vapor deposition, or it is made with the help of spin-on before the photoresist coating. Okay, so you can see here we have the aluminium alloy, we have the dielectric ARC. This is going to reduce the reflections. so as to give me good resolution towards the photolithography. So coming to the dielectric ARC. Dielectric ARC is a PECVD Silane process. Okay, we have plasma enhanced chemical vapor deposition Silane. So what are the source gases? So source gases are Silane, N2O, helium. So we have the plasma and the heat is the requirements for this reactions to happen, and we are forming the oxynitride, so SiOxNY. So after that we have some volatile compounds like H2O, N2, NH3 and helium. So these are all the volatile compounds that are going to vaporize and eliminate from the surface of the chip. So N2O as oxygen and the nitrogen source is used. The nitrous oxide is going to give me the oxygen. So I hope you understood all of the things that I have discussed in this video. These are the references, very amazing book that you can refer for your upcoming studies and for your detailed analysis toward these topics. If you have still any doubt, you can put the doubt in the comment and I am going to revert to you as soon as possible. I hope you like this session. If you like it, please push the like button, subscribe to the channel and also do share it with your friends. Thank you so much.